Okay, thank you very much, Thomas. I believe that you can see the full screen presentation.
Perfectly.
Yeah, great. Just give me a second. Okay, good morning, everyone. It is very nice to have these rounds of webinars organized by Alice. So, Thomas, thank you very much for organizing all of this. Now, this presentation is not about Seamless. It's about the Warrant project and the work that our group at NTUA is doing within Warrant. However, I would also like to stress that our group, and I'm a researcher and a PhD candidate at our group, which is called Maritime Risk Group at NTUA, is dealing a lot with safety and risk assessment for autonomous ships in these past, I don't know, now maybe almost 10 years. And also we are coordinating the Seamless project. So it was interesting for us to also highlight the relationship between Seamless and, for example, Warrant, as well as other projects funded by the European Commission within the context of these webinars. So I will say a couple of things about that very briefly. So Seamless is about seeing, how autonomous ships can be viable from the business perspective within the context of an actual transport service. And Seamless is looking to both the short sea shipping segment and the inland waterway segment. On the other hand, Warrant, and I will say a few things about the project itself as well, is more about the dependability of autonomous ships and in general of what we call Waterborne digital systems. So the relationship there is that in order for autonomous ships to be viable, they also need to be dependable, and dependability involves a lot of different system qualities, let's say, such as reliability, resilience, fault tolerance, safety, all of these qualities, actually. So it's interesting to see how Warrant kind of builds or can exploit some of the outputs from Seamless in order to quantify the dependability of such systems. And specifically, Seamless is doing work in aspects related to the design of autonomous ships, to the approval of autonomous ships, of course, to the guidance, navigation, and control aspects of what our colleagues from Delft have presented, as well as the relationships between cybersecurity and safety in these types of systems. So it's interesting to look at how the two projects can really connect. In this context, now Warrant is a 3-year project. It started last year, May 2025. The full title is Waterborne Federated Systems and Models for Secure and Resilient Operations. And there is a consortium throughout Europe involving, it's coordinated by INLECOM. It involves SINTEF, DNV, DST, VLTN, TU Delft, the Port of Antwerp, Technalia, CFAR, Euler, Connected Thanos Shipping from Greece, and ourselves. Now, our group, within the context of the Warrant project, is working on the hazard and vulnerability analysis method for risk assessment. Specifically, the motivation for this work is that Waterborne digital systems are smart, interconnected systems with shared human-machine and possibly AI control, as well as IoT sensors that exhibit complex behavior when we talk about off-nominal conditions, so when we have faults, failures in safety critical conditions in general. So the objective within the project is to adapt and extend the conventional HAZOP analysis for reducing unidentified hazard scenarios and also improve the effectiveness of safety assurance for these types of digital systems in the maritime domain. Now, I will quickly go through what we mean by waterborne digital systems and why a risk assessment becomes a bit more complicated for these types of systems. So, waterborne digital systems are a subset of what we more generally refer to as cyber-physical systems. And these are types of systems that integrate physical processes and computational components, and they are interconnected. And I should say that they are both connected to the outside world with other systems, and their internal components are interconnected as well. So, cyber-physical systems rely on continuous interaction between sensors, controllers, actuators, as well as connectivity. So, in general, we talk about industrial automation systems, smart transportation infrastructures, systems in the aerospace domain, and so on. In the maritime industry specifically, we can think of, for example, integrated bridge systems or engine monitoring systems. And these are types of systems that support vessel functions, such as navigation, propulsion, cargo handling. And they often include software control and increasingly now artificial intelligence-driven control, IoT sensors, so connected sensors to the outside world, as well as more generally automation technologies. Now, all of this is very nice because cyber-physical systems in general improve efficiency. They may reduce costs with all the automation capabilities they provide. But in terms of risk and safety, assessing the risks related to these types of systems becomes a bit more complicated. And this is because the interaction of their components derive more new hazards and new ways that the systems can fail. So now communication delays become important. Incorrect sensor data becomes very important for maintaining safety. Also, cyber threats can directly trigger safety critical failures. So a cyber threat can impact navigation, propulsion, cargo management, and a cybersecurity breach can have physical consequences in terms of loss of human lives, damage to the environment, and to property. And finally, cyber-physical systems, which include machine learning and AI, as well as distributed control systems, they have a dynamic and possibly black box behavior. And this complicates risk assessment in the sense that it's not easy to see what the consequences of a wrong decision or of a failure can be, and what are the causes of that hazardous scenario, let's say. So within this context, focusing on the hazard vulnerability study, and let me say that the HAZOP method is chosen because it's an established hazard identification technique in the industry, although it originally came from the chemical process industry. But it has been standardized in the latest EX standard from 2016, and is a method that is frequently referenced in, for example, guidelines by the classification societies, as you can see here from a recommended practice from DMV related to risk management in marine and subsea operations. So HAZOP is a tool that is being used from the industry. And its fundamental principle is that hazards arise when the system deviates from its design intent. So what the designers intended for it to do and what the designers intended for it to behave. And the process that is typically used for doing a HAZOP study is that we gather a group of experts who have a broad understanding of how the system works. We gather information about the system, so we need to know its architecture, how it does what it does. And then we try to segment the system into little manageable pieces called nodes. And these can represent different segments of the process that the system is involved in, or different operational functions of the system. Then once we have the nodes, we apply what is called guide words. So these are, let's say, types of these deviations that can occur in the nodes. So we have guide words like no, more, less, part of, other than, and these are used to identify hazard scenarios. And by scenario, we mean that we are also interested in examining the causes of a deviation as well as its consequences. Now, traditionally, HAZOP in the maritime domain has been used for systems such as inert gas systems, ballast pump systems, or fuel supply systems. And these are typically or traditionally less complex and predominantly hardware-driven systems. Also, HAZOP does not inherently account for cyber attacks and software-related failures. And since, because HAZOP is focused on single-point failures, it kind of fails to capture the hazards arising from the interactions between the components. And as I mentioned earlier, it's not easy to determine a deviation from the design intent when we're talking about complex adaptive systems that include machine learning and AI. So we have all these different challenges for risk assessment related to complexity, to risk propagation, cybersecurity, and human-machine interactions. Now, from a literature survey that we're currently doing, we have identified several different approaches that have been used to address these types of limitations. So there are variations of HAZOP, like cyber HAZOP, that focuses on cybersecurity. For control, called control HAZOP. Then we also have hierarchical approaches that look at the system at different levels of abstraction and do multiple HAZOPs and then combine the results. Then we also have model-based approaches which use mathematical models and simulations to identify hazard system states, causes, and consequences. Now, specifically in the warrant project, HAZOP is kind of used as the bridge between what can happen at the component level as a failure and to determine what can happen to the system at a functional level. And this is done by a knowledge graph that is being developed within the project by Connecta, and it kind of glues everything together. And this is also interwoven with the concept of dependability, which is the end goal here to quantify the dependability of Waterborne digital systems. So in general, in Warrant, there are 4 living labs that for the work we are doing with HAZOP provide case studies for different types of Waterborne digital systems. And what I will present in the next slides is an initial case study that we're doing within a specific living lab in Warrant. Now, we're talking about the 4th living lab. This is about dependable remote operation systems. And the stakeholder there is CFAR, who are also participating in the project. Now, in this living lab, the operational environment is remote control barges in the Rhine and Antwerp regions, so inland waterways. The objective is to apply the Warrant methodology to ensure remote operations are safe, cybersecure, and resilient under real-world conditions. And specifically what we're doing with HAZOP is that first, we're selecting risks that are of interest to the stakeholder. So we're trying to ground what we do in actual stakeholder needs. And then we implement HAZOP variations to identify methodological gaps. And this work will provide input to the HAZOP-based methodology that is developed in Warrant. And I will briefly discuss a few points about the case study that we have started doing. So the initial study object that we have selected is the handover procedure, so handing over control from the remote operation center to the ship and vice versa. And as a method, we have selected the procedure HAZOP variation, which is conducted through workshops with CIFAR. And the nodes in this approach for HAZOP are the steps of a procedure. So we have, let's say, 10 steps. Each step in the procedure is a separate node to which we try to apply deviations. So nodes we were interested in the handover procedure is the request by the RC to initiate remote control, the ship requesting to take back control locally, and so on. So in these nodes, we apply guide words such as no, which means that none of the design intent is achieved, guide words such as part of, that only some of the design intent is achieved, so only part of the procedure step is being done, actually. And then we also have a matter of sequence, something happens before or after what it's supposed to do, and issues with timing. Something happens earlier or later than intended. So for each node and for each deviation, again, deviation means a step of the procedure combined with a guide word. We examine the causes of the deviation, the consequences, any existing safeguards, and then we rank the risk level for each deviation. Now, in terms of causes, we're looking in this specific case study into hardware failures and also human factors, so issues of stress, fatigue, lack of due diligence, as well as operational conditions, time pressure. Then with respect to consequences, we are looking at impacts on safety, on assets, on the environment, and on the operation. And with existing safeguards, we are looking to the redundancy that can be embedded into the system, and existing monitoring, alarm systems, or shutdown or control mechanisms. And this is just a snapshot of the type of hazardous scenarios that we are identifying through this process. And just a snapshot because it's a work in progress. So here, for example, we see that the design intent is that before control is handed over, ship controls, meaning steering gear and propulsion, need to be on a neutral position. And there is a design safeguard that the ROC operator and the ship must check that ship controls are actually on the neutral position before control is handed over. And in this context, we are looking at what can happen if the checks are not performed, or some of the checks are performed or are performed later than intended. Now, wrapping up my presentation, I do hope that I have kept the time. What are the next steps? So we want to evaluate how different HAZOP variations can be integrated, if this is necessary. And the goal is to reduce unidentified hazard scenarios that relate to the CPS-like characteristics of remote operation systems, for example. Then we'll conduct similar case studies in the other living labs. And all of this work will support the structure of the warrant knowledge graph with knowledge of change of events. So this is what comes out of the HAZOP process. The chain is starting from causes, going to deviations, consequences, and then what is the impact on system functionality. And finally, within warrant, we will examine how the methodology can support the safety assurance process for different types of waterborne digital systems. So thank you very much for your attention, and I'm available for any question. Thank you.